Recording here. Hello, my cool cats and kittens. How are you guys doing? So this is it, the day that the stars finally align again. As of today, both classes are going to be in the same place. Yes, cats and kittens. It was Kevin's homework to figure out where that was from. Let's try to get this lecture right. I actually did this lecture before for the other section, and the technology was just not working with me that day, which, you know, by the way, whose fault is it? I just like to say I take no responsibility for this. I think I did a fantastic job. If there's one person to blame for how things went down, it's Carol Baskin. Carol Baskin is to blame. And yeah, but we will make it through. Well, I'm kidding. You know where it's from? It's Carol, man. Yeah, Carol with an E. Yeah, but yep. As of today, hey, allegedly, I don't want anyone from my class throwing out accusations here. That's not what we're about. Allegedly. Okay, so okay, so yeah, today's class is mostly on, let me share the screen. Ta-da! Polar coordinates. And in the meantime, just to make sure things are running smoothly, not taking any chances, even though technology that I'm working with right now is a lot better, I'm going to turn off the video whenever I'm sharing a screen. So yeah, and another thing I wanted to mention is that I was watching the YouTube video to make sure it wasn't freezing again or doing anything really crazy. But I realized, to people who are actually not in this class, it seems like I might have like multiple personalities or something, because sometimes I'll be talking about one thing and then I'll just go off on a tangent and blurt something out. Like I'll be talking about, oh yeah, well, you know, the angle here would be pi over 4. Oh, by the way, I'm not teaching in the fall. And people who are listening and don't actually have access to the chat window, they're like, what is Jhevon talking about right now? Yeah, so sometimes when I go off and say something completely unrelated to what I was saying, for the benefit of those who are not in the class and are not seeing the chat, I'm not getting crazy. I'm actually responding to something that someone is typing. I liked it when you guys used to talk, then everyone would hear you and know that I'm not just talking to myself, but everyone seems to be into typing these days, which is fine. As long as you're all here, you're all safe, I'm happy. We are going to talk about polar coordinates, and we are going to keep it pretty light today. So again, the subject matter of today's class, not going to be crazy hard or crazy difficult, but well, you wouldn't be interrupting if I pause and ask for a question. And now you're starting to make me look crazy again, because I was going off into my lecture and you had to type something to make me respond. Okay, so we're going to cover some basic things in polar coordinates. There are even some things here that I prepared that I will probably skip over, because in the grand scheme of things, it's probably not that important for you to know this right away or ever, actually. 11.4. There were two things that are in a typical Calculus 2 class. I'm not sure. I feel like I mentioned this already, but I don't remember to which class. There are two things in a typical Calc 2 class which are essentially useless. And a couple of them have been thrown away from this course, which I agree with. The first thing is there was a topic that's normally taught called volumes of revolution. That's normally taught in Calculus 2. The thing is, once you go into Calculus 3, you find a much more efficient way to find volumes that you never use the method that you learned in Calculus 2 ever again. So while that topic was cool and it was a lot of fun, it's a lot of fun to teach, it's a lot of fun to do the problems, you never actually really use it. Even in mathematical spheres, even in academia, it never shows up, not even in theory anymore. The other thing is graphing polar curves. So talking about the graphs and the calculus of polar curves, like the only place I've ever seen that, the only place I've ever known that to be used was in a Calc 2 class. Once you actually leave Calc 2, no one talks about this, as far as I know. Maybe there's some obscure applied mathematician out there who does this stuff. But polar coordinates is important. There's a lot of important things that we need to know about it, especially conceptually. But in terms of how to graph polar coordinates, polar curves in 2D, they are pretty cool graphs, but we're never going to use it beyond this class. One thing I would say is that maybe during this week off that I'm giving you guys, I might just post an optional lecture where I talk about this stuff because it's really cool. You might want to see it. But for the most part, I'm going to skip over 11.4. It's not in our official syllabus. It is something that I've taught in the past, but even I kind of feel like, yeah, this one, it's not even worth covering. So while things being left out of the syllabus isn't a reason for me to not cover it with you guys, because you guys know, I tell you guys what I think you need to know because I want you guys to be the best out there. I want you to be my math ninjas, but some things really just are useless and you never use them again. We're going to cover 1.3. That's going to be pretty much all you need to know about polar coordinates. Again, very basic stuff. After that, we're going to talk about conic sections. And again, a lot of conic sections we don't talk about beyond calculus 2. So right now, when I talk about conic sections, the focus will really be on graphing them because we actually do use the graphs of certain polar functions. When you go into Calc 3, and even in this class, when you start to go into graphing, it is going to turn out that in order to graph things in 3D very well, you're going to need to know how to graph things in 2D very well. And so being able to graph things like ellipses and hyperbolas and all that stuff, that's actually going to be useful in the future. Being able to draw a cardioid, not that much. Being able to draw a flower with intersecting petals, not that much. But being able to draw conic sections is going to be very important. So let's actually jump into it here. We're going to start with 11.3 polar coordinates. And as you see here, it is a new way to look at the world. So basically what I'm talking about is coordinate systems. So remember what a coordinate system is. It's actually just a way in which you talk about the location of things in a given space. So the space that we will be using will be the Cartesian plane, right? The XY plane, as some of us call it, invented by Descartes in the 1700s. That is our space. And now we want to talk about ways that we can locate things in this space. And normally we use what's called the rectangular coordinate system. So this is the coordinate system we've been using this whole time up until now. And you guys are all familiar about it, but I'm just going to go over a few simple things just for comparison's sake when I teach you about a new coordinate system. So we're used to seeing the rectangular coordinate system. Now, in the rectangular coordinate system, and remember, a coordinate system is just a way to locate things in a space. We locate things based on where they end up on the vertex of a rectangle. So if I am drawing the XY plane here, right? And I want to say something like, locate the point 1, 5. What do we usually do? Well, we know that the origin here is where X and Y are 0. And we would move 1 unit on the X. We would move 5 units on the Y. And we pretty much draw a horizontal line emanating from the 5. We draw a vertical line emanating from the 1. What you'll notice here is that we've created a rectangle. And the vertex opposite to the origin is the location of the point. This is the point that we call 1, 5. It is located based on the fact that it showed up on the edge of a rectangle. Similarly, if I were to figure out the point 3, 1, I could do that. I end up having to draw another rectangle. And the vertex opposite the origin is the location of this new rectangle, of that point, the coordinate that we call 3, 1. Now, when it comes to negatives, essentially what I want you to realize is that for us, a negative really indicated a change in direction. Instead of moving right on the x-axis or up on the y-axis, negatives really mean we would move left on the x-axis or down on the y-axis. So if I wanted to locate the point -2, 3, I would move 2 units, but on the left from the origin, that's our -2. Then I would move 3 units down from the the origin, and that creates this rectangle. So the negatives really come with a change in direction. This is the location -2, -3. But this is the rectangular coordinate system. You basically locate things based on rectangles, essentially. So now we want a new coordinate system. We want a new way to talk about locations in the plane. And you might say, why do we need a new way, right? So remember, every time we've done this, students have the same complaints, right? When we talk about exponentials and now we like, oh, let's invent this thing called a logarithm where we kind of invert the exponential. Why do we need that? What's wrong with exponentials? But of course, you inventing something, looking at it a different way, has so much benefit to it. There's so many things that we get from calculus just by knowing about logarithms. It's that if we hadn't invented that thing, we would have been worse off for it. So just because you know about one way to do something doesn't mean you shouldn't always continue to explore what's out there, different ways of looking at things, different points of view. In mathematics, that is a good idea. Instead of yeah. So coming up with a new way to look at the world is useful. I'm laughing at comments here. So if you're not in the chat, don't think I'm crazy. Okay, so basically how we're going to figure things out is we're going to use circles instead of rectangles. And so essentially what we want to do is, so here there's some random point in the plane. Now, instead of thinking about it as being on the corner of some rectangle, what I want to do is find a circle centered at the origin which has this point on its circumference, right? So you have this point lying out here. What you're going to do is, can we think of a circle that's centered at the origin that this point is going to be on the circumference of that circle? Now, of course, once we do that, we'll automatically have a distance going from the origin to that point coming into play. And we'll also have an angle that we can make with a positive x-axis. We call these distances r and the angle theta. And so basically, instead of locating a point based on where it shows up on a rectangle, what we do is we now consider two different numbers that's going to measure where a point is. The numbers r and theta, which we usually put in this order. And so how can I get to a point? Well, tell me what angle I need to make with the positive x-axis, then tell me what distance I have to run along that angle with a straight line from the origin to hit that point. Tell me these two numbers and I can tell you the location of your point. So r is the distance from the origin, theta is the angle made with the positive x-axis. So just as how we can locate points using their x and y coordinate and a rectangle, we can now locate points using the r and theta coordinates and circles. So we really want to think of the universe as a bunch of concentric circles as opposed to a bunch of rectangles with a common point, the origin. And that's basically the idea. So once we have that idea, that's how we want to look at the world. Now we're going to explore what are the consequences of looking at the world in this way. But before, of course, we do that, let's actually just locate some points using this new coordinate system. And here you'll see in the notes, I kind of explain just kind of the verbiage that we use here. So the system that locates points in this way is called the polar coordinate system. And if I want to refer to a point that was used in this system, we refer to it as a polar coordinate. So we're used to just coordinates or the XY coordinate, but here we're talking about the polar coordinate. Oh, this is way out there. Not exactly. Not exactly. This does have, so I'm responding to a question here. You'll definitely use this kind of notion in the development of wave functions for sure, because thinking in polar coordinates is very useful for the complex plane and differential equations and a lot of things that we would use in wave functions. But I wouldn't say this is directly responsible for it. But yeah, so yeah, it's just a new way that we want to locate points. And we're going to see some of the cool things. And in Calc 3, you're going to see a lot more cool things that come from us being able to locate a point this way. Now, let's locate the point r theta equals 1 comma pi over 4. Well, what that would look like, of course, a pen here. So I want to locate it in the xy plane as normal. So we're looking in the xy, but instead of thinking of this as an x and y coordinate, I want to think of it as an angle and a distance. Basically, what this is saying is I want to make an angle of pi over 4 with the positive x-axis, and along that angle, I want to travel from the origin a distance of 1 unit, right? And so this is the point r theta equals 1 comma pi over 4. Is that clear? Any questions so far? Okay. So no questions so far. So as far as some things that should be obvious, but they need to be pointed out at this point, is the fact that now in the polar coordinate system, points or locations do not have a unique representation. Why is that? Well, if I were to go around 2 pi and then come up with pi over 4, I would actually go along the same angle. And then I could actually go around a whole other time. I could go around and around and around, cover 2 pi's, and then end up at the same angle again. So notice that this coordinate here is actually going to be equal to, this is actually going to be the same thing as if I were to go a distance 1 after going around 2 pi plus pi over 4, so 9 pi over 4, right? This will also actually be equal to, if I were to add another 2 pi to that. So it's like 1 plus 8, 17 pi over 4, right? All of these coordinates here in the polar coordinate system, they are referring to the same location. And that's because we know about angles that you know, they all have reference angles, and they all, in terms of location, they overlap and repeat on themselves. You can, if you go around in a full circle, you kind of end up back where you started. So because our system of measurement now involves angles, we can essentially have a list of redundancies that are arising from this. So that should be clear. So for any coordinate r comma theta, that is equivalent to r comma theta plus 2n pi. Every time you add 2n pi, you end up along the same trajectory. It's not going to change your direction, really, right? So this is just mod 2 pi. Anything larger than 2 pi, you can kind of just use the reference angle instead. So that's one thing I want you to know. Also, there is another convention that I want you guys to be aware of. So remember how in the rectangular coordinate system, a negative meant a change in direction. Normally, if you have a positive x and positive y coordinate, it means you move to the right and up. If you have a negative x or a negative y coordinate, it means you should move to the left or you should move down. Polar coordinates also has a directional thing when measurements become negative. Now, of course, if an angle is negative, we know what that means. It just means you measure the angle clockwise instead of counterclockwise. But what would it mean for the r to be negative? Every now and then in a polar coordinate system, you will just have a negative r value just arising. But what does it mean to be a negative distance from something? Essentially, it just means a change of direction. Instead of moving towards the thing, you want to move away from the thing. So let's look at this guy, minus, yes, you graph the reflection over the origin. Exactly right. I'm in red ink here. So essentially how you can think about this is you have your XY plane and you have that angle pi over 4. Now, normally your trajectory would shoot out at the same angle that you've just opened. But whenever you have a negative r value, what you do in that situation is you're actually going to the exact opposite direction, which, yes, a very good way to describe that is a reflection over the origin. So instead of moving 1 unit towards the pi over 4 angle, you actually move 1 unit away from the pi over 4 angle. So this point over here is going to be your -1 comma pi over 4, right? Whereas the point over here would have been the +1 comma pi over 4. So when your r is a negative value, it really means you interpret that as a change in direction or a reflection around the origin, or just going the opposite way in which you thought you were supposed to go in the first place. That being said, you can notice that I could have hit, there is another representation of this point, 1 comma pi over 4, that doesn't just involve me changing the angle, but I can actually change the angle and the so another way to actually look at this at the same point, if I wanted to get that same point, one way to accomplish it was I could have gone around here, right, which is running along this, right? So this would be the angle, this would be 5 pi over 4. So this is 5 pi over 4, right? Because this 180 is 4 pi over 4, then you add another pi over 4. And if I make the r value negative, it will actually push me back over here where this angle is pi over 4 to this point. So the 1 comma pi over 4, it's actually also equal to, if I were to say -1 comma 5 pi over 4. Right? So I can take, so I have a list of angles that would go along with the r value 1, but there's also an infinite list of angles that would go along with the r value -1, and I can actually locate the same point by actually doing this. So that's something that you should also be aware of. So it is possible for us to have quote unquote negative distance being applied here, but you just think of that as a change in direction, a reflection over the origin. Instead of moving towards the angle, you go away from the angle. Yeah, so as you can see, these are all going to be the same. So I don't know if, well, I actually did all of these individually. So yeah, if you have 1 comma pi over 4, that's this point here. It's actually the same as 1 comma 9 pi over 4. And that's actually the same as if I were to do 5 pi over 4 and then -1. So I go back in the opposite direction. These will all hit the same point. So multiple ways you can express a location in this coordinate system. However, that's just one of the things we have to take with it, the good and the bad. But it's still a very useful system either way. Just have to be careful because we're involving angles here. Things can kind of get redundant. There will automatically be redundancies put in here. But sine and cosine have redundancies, but they're still pretty darn useful. So we can't just get rid of something just because it might have redundancies or overlaps. That being said, we also have, because we're all great at trig, we also have some formulas that should come up right away. It should be clear right away. The moment you start to talk about circles, there I go in the green ink again. The moment you start to talk about circles and angles, you automatically will have trig come in. So if we're talking about this guy, theta and r, automatically you might realize that, hey, I can just create a vertical line hitting that point and a horizontal line hitting that point, essentially trying to get your x and y back into the mix. And you might want to be able to talk about this point in polar coordinates, but you might want to be able to translate from your usual rectangular coordinate system to your polar coordinate system. And trigonometry ends up being a very useful thing for that purpose. So of course we know that cosine is adjacent over hypotenuse, so that tells you that your x is r cosine theta. Sine is opposite over hypotenuse, so that tells you that your y is r sine theta. And again, this you should also recognize as an overlap from what we were looking at with parametric equations. It's just that our h and our k in the parametric form is actually 0. So this comes from the typical r cosine theta plus h, but except here your h is 0 and your y equals r sine theta plus k, but we let k equal 0. So these are the same guys you can think of as from yesterday. Right? But yeah, these equations are immediate. Of course, it also stands to reason that x squared plus y squared equals r squared. You can get that by Pythagoras' theorem, or just realize that this actually lies on a circle of radius r, so your x and y must actually obey the equation for the circle of radius r. As well as, notice that your opposite from theta is y, your adjacent is x. Opposite over adjacent is the tangent. So if you take the tangent, you would get y over x. And essentially here you have infinitely many values. Right? Every time you find a solution, if you add 2 pi to it, you also get a solution. And by the way, notice that if you add pi to it, you'll also get a solution, but that gives you the solutions for the negative r's. But essentially you can solve for theta if you ever need to by taking the inverse tangent, and just by paying attention to the quadrant. Be careful to pay attention to the quadrant. Because infinitely many values will work. Okay, but yeah, we have these two sets of equations, very important equations. They follow directly from trigonometry, but also it's worth noting that this pair of equations here is very useful for converting from polar coordinates to rectangular coordinates. So if I know the r and the theta value, I can plug into this to compute the x value. If I know the r and the theta value, I can plug into this to compute the corresponding y value. The second pair of equations, this is useful in converting from, I think I should highlight this. Right. So these are useful in conversions. Every now and then you might want to jump between coordinate systems. Sometimes because a problem would be given to you in rectangular coordinates and you want to translate it to polar coordinates to make it easier. We might talk about that in a little bit. Or vice versa. For some reason, you might want to switch between coordinate system, and these equations are going to help us. And in fact, that is the next set of examples that I actually want to cover, switching between coordinate systems using these equations. So let's actually do that. Hold on, let's see. I think we lost some people there. Okay, so let's actually do some equations like that. Suppose we have r comma theta is equal to 2 comma pi. Maybe someone want to walk me through how do we convert to xy coordinates? So this is where you guys come in. 2 cosine pi, that would be what? That's the x. So your x, you know, is r cosine theta. This just becomes 2 cosine pi. What is cosine of pi? -1, so it's -2. And your y would be r sine theta. So that's 2 sine of pi. Sine of pi is 0. So this actually translates to the point -2 comma 0. And that makes a lot of sense. If you are at an angle pi, that's the angle pi. And then you move 2 units from the origin, that puts you out here. So we are at a distance 2 from the origin, so this gives us -2. So -2 comma 0 is the point that we are after. So that's okay. And so conceptually, not a big deal here. You just have to remember your trig. Of course, you always have to remember your trig. If we look at r theta, the coordinate r theta equals radical 3 pi over 6, then this would mean that your x is r cosine theta. Cosine of pi over 6 is? No quick responses here. Right, this guy here is radical 3 over 2 times the radical 3. So this is 3 over 2, and the sign is a half. So it's radical 3 over 2. And so this gives us the coordinate. So this is the xy coordinate. So this gives us the coordinate xy would be 3 over 2 comma radical 3 over 2. And so yeah, so all right. How do we go? Now we're going to do the opposite. How do we change the points 1, 1 and 0, 2 to polar coordinates? So here we have our xy equals 1 comma 1. How do you change that to r theta? Right, so we're at this point over here. This is the point 1 comma 1. We pretty much need to figure out an angle and a distance that will hit that point. Right, so your theta is tan inverse of y over x. This is just tan inverse of 1, which we know is pi over 4. And this is in the first quadrant, so that's fine. And so also your r is pretty much the square root of x squared plus y squared. Now, technically speaking, you could have a plus or minus here. How do you actually deal with that? So this gives us a plus or minus radical 2. Right. So because we're in the first quadrant, take the positive distance. So your answer here would be your r theta is radical 2 pi over 4. Could anyone give me an answer with a negative r? Also possible. Right, you can have -2 5 pi over 4. Right, you would have an infinite number of answers, but of course you normally go for the easier one unless there's some actual reason in the problem that you're dealing with where you don't actually want to take the low-hanging fruit here. But yeah, that's that. Let me move this. Now, this set of examples that I have here that I'm moving down to give us some space, these are going to be really important, especially in Calc 3. You're definitely going to use that a lot. But let's just get through another example here. 0, 2. So we have xy equals 0, 2. Can you tell me what the answer is just based on the location? No, that's 0, 2. Here's 0, 2. Yeah, 2 pi over 2. So you can actually start to see right away what an answer is going to be. 2 comma pi over 2 is going to be how you're going to do it. Now, if you were, so by inspection, if you were to actually compute this, you would have your theta would be tan inverse of y over x, right? But notice that your x is 0, so this here is undefined, right? So that should tell you, hopefully if you remember your trig, that would imply that your theta is, more generally, it means it's an odd multiple of pi over 2, where n is odd. But you can just take theta equals pi over 2, just take one of the easy ones. And then, of course, here you'd have your r is equal to the square root of 0 squared plus 2 squared, which is just 2. And so, again, you would get r theta equals 2 comma pi over 2, right? Or you could do minus 2 comma 3 pi over 2 or something like that as well. 3 pi over 2 is going to be another angle where your theta is going to be undefined, where your tangent is going to be undefined. Your theta would actually have a value. Yeah, so that's that. Now, of particular convenience, this is one of the things that's going to make it very convenient for you in Calculus 3 to use polar coordinates. And by me just talking about it with you here, you're probably not going to appreciate how this is going to save your life so often. It's going to seem like some very simple things, but just knowing how to envision and describe a region in the plane in terms of polar coordinates is going to be so useful. Isn't it just strictly better in 3 dimensions? No, it's actually, depending on the situation, you can get things to be easier in 2 dimensions as well. And I'll probably do a few examples, rush through a few examples later where I'll show you that's the case. So in 3 dimensions, when we start to talk about polar coordinates, we actually call it cylindrical coordinates. And I guess you have to just stick around till 213 to know what that is. I might mention something, but it's above our pay grade at this point. One useful thing with polar coordinates is to be able to describe regions in the plane. And of course, whenever the region you care about is, especially if region is circular disk shape or part of a disk, right? That's when it's very useful, right? Because our polar coordinate system automatically has us thinking in terms of circles. So that automatically means when you have any kind of circular region, it might be to your benefit to be able to describe it in polar coordinates as opposed to in rectangular coordinates. So describe the region in the plane bounded by the quarter circle in the first quadrant and this equation, right? So essentially what we want to look at is this region here. Circle of radius 3, and we want to talk about this guy, right? Now, on one hand, you could describe this in rectangular coordinates. So so we can compare. If you had to do a rectangular description, how could you describe this region? Well, you could say, well, I want our x to be greater than or equal to 0, comma, and I want our y to be greater than or equal to 0. That tells me I want to be above this and above that. And I also want my y to be less than or equal to the positive square root of 9 minus x squared. And that tells you I should be below this at the same time. So I can use 3 inequalities to describe this. More than that, notice that this inequality includes some radical function, which automatically could could bring with it some challenges in a more complicated problem. But how would you go with the polar description? So anyone want to take a shot at this? Give me an equivalent description like this, just inequalities to describe this region, but in the polar sense. Well, you wouldn't say r equals 3. R equals 3 is literally the outline. R equals 3 is along this line. Yeah, it's a region. Right, r is less than or equal to 3. Now, normally, that will be good enough for us in if we were in Calc 1 or lower. But remember, technically, our r value can take on, right, so that's how we need to fix it. Force it to be greater than or equal to 0, and just make sure that it's less than 3. How can we restrict the other variable? Right, 0 to pi over 2. So notice here in the rectangular description, it took 3 inequalities to describe this region. And just for me to say what's going on with the x and y, I took 3 inequalities. One of them is actually a pretty complicated inequality. Compare that to the polar coordinate description. I can describe what the 2 variables are doing in 2 inequalities, and they're 2 very short inequalities. In fact, it's constants. One way you can think about this, and again, this is slightly above our pay grade, but what you can think here, because the angle starts here and moves to there. So here your theta is 0, and here your theta is pi over 2. But you want to cover all points between 0 and pi over 2. Right. Now, one way you can think of this is that in the polar universe, I mean, we live in the XY plane, right? So we are seeing a quarter circle, but in the polar universe, we're really actually looking at a rectangle. If we were plotting r versus theta, that circle will look like a rectangle, right? Now, describing this region in rectangular coordinates requires us to think of this thing as a circle and hence use the equation of a circle. However, if I imagine this in a different universe, right? Like if you were to Twilight Zone, change the universe where your reality warps into something else and your universe follows different laws. In this new universe, what we're looking at is a rectangle. And when you get to Calc 3, you're going to appreciate that a lot because Calc 3, how we're going to set it up, it's going to be based on rectangles. And so if we're in a situation where we don't have a rectangle and we have a way of thinking about it as a rectangle, that automatically is going to make our lives a lot easier. So that's just one thing. So very, very important that we are able to do this. And it's also nice that it is actually a lot easier to do than it would have been to do it in rectangular coordinates. Yeah. What about these? Hold on. I guess I can move this down a little bit. Yeah. Hello? Someone trying to say something? What about these here? These three places here. Okay, maybe three different people chime in here. Someone describe this one, someone describe that one, someone else describes this one. Okay, David volunteered to describe the first one, according to the chat. And Kevin volunteered for this one. And who wants to do this one? Yes, okay. So we're David's doing this, Kevin's doing that. You want the third one? Okay, Kevin, David. Well, Evan's been chiming in. Evan, you want to take this one? Is Evan still around? Sure, okay, Evan. All right, I'll give you guys like 3 minutes. Let's go. Oh, David is already on it. Okay, all right, let's hold on here. David's already putting in his answer. Let's get some space here. Okay, I'll still wait for the 2 minutes for the others to do it so that they can pay attention while I'm doing this. So let's give them 2 minutes to come up with the answers. Also, come with a description for what the picture would look like. Yes, looks like a washer. Right, so the mathematical phrase for that is annulus. Yeah, it's so close, but yet so far. You know, like when they're talking about, oh, what do we call it? And he starts writing out A, N, N, U. And someone was about to make a dirty joke, and then they just ruin it with the last part of the word. Hey, that kind of looks like an, of course, annulus. Why not? Yeah. The only time math people get descriptive and creative with naming is when they want to prevent something like this. All right, let's move. I think our time is up. So, okay, so let's start with David. David already has his answer up here. He says it looks like a washer, and that is correct. So this is when you have two concentric circles, and you actually care about the region in between them. So we care about this region in here. Right, so the region in between two concentric circles, this is called an annulus. And we have here a circle of radius 3. So this is x squared plus y squared equals 9 right here. And then the inner guy, oh, I have the big eraser. I should have put the small eraser. Ah, okay, let's start over. And there's an inner circle, and that guy is your x squared plus y squared equals 1. For some reason, there are a lot of people shouting outside my window. I don't know what's going on. So like a lot of cheering and people. What's going on? Was something just announced? Yeah, I know, but they're not all watching this video. Are you sure? CUNY declared all pass? I don't know. I need to find it out. Okay, so at 7:05 p.m., something happened. After class, go check it out. Not right now. Yes, Ash is back. Anyway, yeah, it's a good that you're here from RS2 because this video on RS2 has really a lot of issues with it. Things were freezing a lot and yeah, was okay. So we have the annulus. So the annulus is, this is just the region between two concentric circles. Let's get back on track here. I got distracted for a while because there's a lot of noise going on. People are knocking on pans and cheering and stuff like all out of a sudden. Yeah, I do send out invites to every single time because I don't know who can attend which lecture. I don't know what situations you're all in out there. So yeah. Hey, if Ash wants to attend every lecture twice, I'm okay with that. You've invaded our lands. Okay, so yes, so notice here talking about your R value, you want it to be less than or equal to 3. That's the distance from the origin. But you want it to be greater than or equal to 1. So that's actually the description. I wanted the 1 here. So that's the R description. Now, essentially, notice here, we could have even left this said. Well, not so much. Let's not say it that way. Because I'd probably want to say we could leave theta unbounded. But let's actually just bound it. So pretty much once your theta covers a range of values greater than 2 pi, we would be fine. But let's go 0 to 2 pi. Now, of course, if I had restricted the theta to say 0 to pi, you'd only get the top part of this annulus and so on and so forth. And if you didn't want the outer edges to be included, of course, you change these equations from less than or equal to less than. Yes, now let's look at Evan's problem. It is the semicircle with radius 1 above the line y equals x. Not exactly, there are two. I hope you didn't misread this. So you have y greater than or equal to x and y greater than or equal to minus x. It's like the slice of a pie, P-I-E. Yeah, yeah. It's a David joke. Yesterday, David typed P-I-E instead of pi. Yeah. So we had one equation, which is like, that should have gone through the origin. I wonder if I can, So you have this line, y equals x, and then you had another line, y equals minus x. You wanted your y to be bigger than this one, and at the same time bigger than that one, and at the same time less than or equal to the circle of radius 1. So essentially we have this region here, a slice of pi. Describe the region in polar coordinates. Okay. Wait, did Evan describe it already? Oh, he did, way up top. Yeah, but I don't think you saw the answer that you have. I scrolled up and looked at it. That would be true if you ignored the y equals minus x part. Yeah, so now your theta is between 3 pi over 4. So your theta is between pi over 4 and 3 pi over 4. Your R value is what? Less than or equal to 1, greater than 0. So that would be how you describe that. Going down to Kevin. So this guy is just straight up a disk. This is why Kevin opted for the last one. So it is literally just a disk of radius 4. So yeah, your theta goes between 0 and 2 pi. Your R goes, all that is from 0 to 4. Yeah. Now this, believe it or not, is going to be super important. In Calculus 3, you're going to do something called iterated integrals, where you're going to have like a bunch of integrals stacked on top of each other. And so it's not like x, y, cosine, z, whatever, dx, dy, z. And you're going to be able to have like numbers on here. Wait, I need to pay attention to what I'm doing. So you can't have the x on that. So whatever, something like that. Okay. And pretty much to interpret what this integral means, you're going to have to translate what the numbers on here are as a region in your 3 space. That is going to, and the first 2 guys out here are actually going to be interpreted as a projection region in 2 space. So being able to describe this region based on limits or bounds on a variable is going to be very important. There are going to be times where we're going to have like dr and d theta, and we're going to want to be able to say, oh, the theta values go between 0 and 2 pi, the r values go between 0 and 4 of blah. And normally we'd have an r here, but not always. And yeah, so being able to describe this region to that will actually tell you how to put the numbers on your integral signs. So that's actually where you're going. This is one of the reasons why you need this. So what we're doing now, yes, it's pretty basic, but in the grand scheme of things, there's a much bigger scenario in which we want to be able to operate here. And I'll leave this up here for the people who weren't in this lecture to be totally confused by like, what was Jhevon talking about over there? So yeah, that's coming. That's next semester. And a big part of doing this, like if you guys think integration is hard now, just wait. There's going to come a point where the stuff that we're doing now is going to be the easy part. Just actually setting up the numbers on the integrals to start the integration process. That's what's going to be hard. And a big part of that is finding out what region is this integral talking about. You'll need to know how to sketch it, and you want to be able to draw it. And when you're putting things on integrals, you would much rather have constants on these integrals than to have something like this on those integrals, right? You don't want to have this on your integral. That's not going to be fun. So yeah. That being said, yes, so 11.4, I might just do a video where I talk about this stuff and just post it during the week that I'm giving you guys off, which, as I mentioned, from now until the 15th, we're just skipping. Okay, so we continued through the recalibration period, so I'm giving you guys so that I could give you guys a full week off. And so from tomorrow to the 15th, well, technically from tomorrow to the 14th, I will see you guys again on the 15th. So what's SBS? Yeah, on the syllabus is the 16th. So no class, April 8 to 15 to 14. Next class, is math 212GH, April 15th, which was the old tax day, 6 p.m. Oh no, 11.4 is not in the syllabus. Yeah, for a second I thought it was myself, but then I looked on the math department. Let me double check, because I did check this before. I'm looking it up now. So 212. Let me look at the official syllabus. Yeah, 11.4 is not on there. It's just 11.1 and 11.3. So I spoke about 11.2 because I actually think it's really, I don't think that should be skipped. And it's something that I think it would be to your benefit to know about it before you actually hit Calc 3. 11.4 is completely optional though. In the old syllabus, we used to do that, but we don't anymore. And it's actually something, to be honest, it could be skipped entirely. Like I actually don't see this stuff being used anywhere. It's actually really cool, that being said. I mean, like even check out, who do I want to check out? Like even check out this guy, r equals 1 plus 2 cosine 3 theta. You know what that guy looks like? Let me show you guys what that guy looks like. So you look at that guy, what was it? R equals 1 plus, notice that it's told you r equals 1 is a circle, right? Which makes sense to us now in our concept. When you type this into graph.tk, it knows you're talking about polar coordinates once you say r equals 1. But let's actually go r equals 1 plus, do we say cosine of 3 theta? 3 theta. It's like a flower thing. It's a 3-petal flower. I don't know what that line is about. If we do something like put a 2 in front of this, now you get a flower with inner petals, right? Which is, yes, on one hand, that is pretty cool. But yeah, I don't really see us ever actually using. So hold on. Control the S. And we're back. So if you look at this, Control V, this guy here is actually r equals 1 plus 2 cosine 3 theta, right? So there are a lot of cool things that you can draw from this, and this isn't even one of the most complicated functions you could even draw with one of these things. But wait, hold on. But yeah, so in this section, I would actually teach you guys, why don't I see the chat box anymore? Well, Ash seems curious about this. I will post a second. I'll post another lecture where I actually go through this. But for now, I want to skip 11.4. It's not in our official syllabus, and I'm sad to say I don't really see it being important at all. It's really cool, but I've never, you know, I have a couple math degrees. I've never had to use this ever again. I've seen it in Calc 2, and that's literally the only place I see it. So might record extra optional lecture on 11.4. For now, we're skipping. Yeah. So essentially, what I want to do now is actually move to another topic called conic sections. And for some reason, the chat just wasn't appearing. Let me try this again. Yeah, I don't know. Okay, let's talk a little bit about conic sections. So conic sections, really cool stuff. Here's actually a YouTube video where you guys can actually check out a few more things. Now, of course, when I put the notes in, that's going to be clickable, but hold on. I agree with you, Nick. I do agree with you. Like the moment this all went down, I already decided what I would want to do, but for some reason, I don't know. In terms of exams, they're trying to come up with some sort of perfect solution, but I'm like, you're not going to get a perfect solution. The kind of thing that I suggested would be the best possible solution. You're not going to get better than this. But City College is really just really concerned about people cheating and stuff like that. So yeah. So my idea was to actually use one of these online proctoring services, and under the current situation, a lot of places are actually giving their services away for free. So I'm like, no one would have to pay for anything. Let's just use this. So pretty much what you would have to do is everyone would have to get a webcam, which you guys might have on your phone or whatever. And so basically, you would have someone watching you take an exam to make sure you're not cheating. That's basically what it is. You pay a service to pretty much proctor people for you online through the webcam. And a lot of places actually do this, actually. So there are a lot of, I mean, you guys probably don't know about it, but webcam freezes. Yeah, but I think that's probably the best solution, actually. I mean, what else are you gonna do? And they're concerned, well, they could have someone behind the camera feeding them answers or something like that. I'm like, yeah, but come on, you're not going to get better than that with everybody in their own location taking an exam long distance. Pretty much having someone proctor them online is the best thing we can do. It's literally the best thing. At least you're seeing them. You know what I mean? I don't know if they want to see your face. I don't know what they will have their own rules, and I'm sure if you want to protect your privacy, they'll protect your privacy. But at some point, you have to prove who you are, and they pretty much make sure that someone doesn't sit in your place and do anything. But yeah, online classes are a whole different thing, and a lot of online classes, that's how they do it. And a lot of certificate programs, that's how they do it. They have these online proctoring services. So basically, your webcam is the proctor. Which is, I think, probably going to be the best thing. Another option is to make everything take home, which they definitely don't want that for the final. And yeah, so I don't know. But yeah, definitely it is frustrating that this is still up in the air. I know a lot of other places have implemented a solution similar to what I'm doing, and I know a lot of my colleagues who are teaching elsewhere. They tell, oh yeah, we started giving exams online like a while ago. So Anyway. Yeah, but one-on-one interview and test makes everyone's life harder. And in terms of knowing, how to prep for exams, like I said, before I give an exam, I would give you like a mock exam to do, so you'd actually know what you're getting into. Okay, now as far as conic sections, let's get on. So let's get on with it in conic sections, because you guys are going all over in the chat. Let's actually just finish this. Now, like I said, conic sections are super cool, and unlike with polar curve sketching, these are actually useful. Your GPS, a lot of global positioning systems actually use conic sections. You have all sorts of, it's applied all over the place. Conic sections actually very, very useful stuff. And this YouTube video might give you a few of these uses, or at least point you into the direction where you can actually see the possibilities. It's a really cool video by cancel. It's a really cool video by, I think it's a YouTuber called Major Prep, where he talks about conic sections. So I would highly recommend you watch this video. I'm not going to go into it. Conic sections, what are they? So pretty much this guy here, this object, is called a cone. So this is called a full cone. Normally what people think of as cones are really half cones. So normally when you think of this guy, you're really doing a half cone, but it extends in the other way. That's a full cone. A guy like this would have an equation something like x squared plus y squared equals z squared. So this is when you're in 3 dimensions, x, y, and z. This equation gives you what's called a cone, a full cone. And the coefficients of x, y, and z really dictate the angle that this cone extends down. That being said, when we slice through a cone with a plane, we can create an outline or a cross section. And so as long as we're not slicing through this thing here, this point, which is called the apex, you can achieve certain outlines that we call conic sections. These guys are familiar guys. For example, if the plane is perpendicular to the axis of the cone, you get a circle. If your plane is oblique to the axis of the cone, you get an ellipse. If it's oblique to the axis of your cone, but it only touches one edge and it doesn't actually cut the other edge, it just literally you'd have this curve extending forever along the cone, that creates a parabola. If you are slicing it parallel to the axis of the cone, this creates a hyperbola. There are what we call degenerative conics. This is pretty much a slice that goes through the apex, right? So you can get a point by slicing through the apex so that it only touches this one point. You can get a line this way, and you can get intersecting lines this way. These guys we don't care about. Well, we kind of should, but the ones I particularly want right now, the ones I particularly want to talk about are the guys up here, the non-degenerate case, okay? And our focus, what I want us to focus on here, and so these are the cases we're going to focus on: circles, ellipses, parabolas, hyperbolas. And the main focus on this lecture is graphing these. I want you to be pretty good at being able to graph these guys. Now, we pretty much know how to graph a parabola and a circle. I'm hoping most of us know that. So what I pretty much want to actually teach you guys from this section is how to graph ellipses and hyperbolas correctly. So we have, I set up some equations here which tells you everything and more about what you would want to know about a parabola. Technically, a parabola is just a set of points that are equidistant from a point and a line called a directrix. So if you have a point, this is called a focus, different from the focus up there. And you have a line, this is called a directrix. and you want all points that are equidistant from this point and the line, you would actually get a set of points looking like this, where the distance from this point to that curve is equal to the distance from that point to the line. The distance from this point to the curve is equal to the distance from the point to the line, right? So you set up something like that, that's how you come up with a parabola. So these are some equations. Here's how you'd calculate what the focus of your parabola is. Here's how you already calculate the directions of your parabola is. Here's where the vertex is. The vertex is the lowest or the highest point. This is going to be your vertex, etc. We don't need to know all that stuff, but I just put it there for the sake of completeness, so you can't say Jhevon never told you what these things are. But yeah, that is how you form a parabola. I would just want you to know how to sketch a parabola. And I'm assuming you're in Calc 2. At this point, if you don't know how to sketch a parabola, any parabola that I could give you, I don't really know what to tell you. So parabolas opening upwards and downwards, parabolas opening left and right, looks the other way. Yeah, so that's all the information. Here is what you may or may not know how to sketch, and I want to give you a systematic way to sketch. These are ellipses. So what I want you to know is, how do you sketch it when a circle is elongated? Now, technically what an ellipse is an ellipse will have two foci. So you have 2 points, and let's say you connect a string to these points. And then what you do is hold it taut with a pencil, let's say. And so you have this scenario here where you have your pencil right here and the string is straight there. Now, if you force the string to stay taut as you just drag that pencil going around, what is going to happen is you will create what's called an ellipse. And it's equivalent to actually a curve that you get by slicing a cone oblique to its axis like that. So now, how do you actually go about sketching that is what I want you to talk about. Now, when it's elongated, the length across here, this here is called the major axis. And the points here are your major vertices. And then you'll have a smaller distance here. This is your minor axis. And the points at the edge of that, that's called your minor vertices, which they're not even listed here. But essentially you want to connect these 4 points. So being able to sketch this is the important part here. Here's how you would actually go about sketching something like this. So let's say we have, let's say our A is greater than the B, which is greater than or equal to 0. Okay, and you have something like x minus h squared over A squared plus y minus k squared over b squared equals 1. This is the general form of an ellipse. Now, first of all, you should know how to get into a form like this via completing the square if these were all expanded and separated. So that's the first thing. But again, that's something you should be able to do since pre-calc. So not going to go over that. Assuming you can get the equation in this form, which we'll actually practice some problems doing that. Notice that here, if the larger number under the x, that means the major axis is along the x. Major axis is horizontal. That means it's going to stretch. Well, I specifically left out the A equals B because if A equals B, you actually get a circle. So I do want to emphasize here that we are, yes, it's written right here, which technically it creates a circle. If A equals B creates a circle, which is a kind of ellipse in the same way that a square is a kind of rectangle. So I'm specifically caring about, I don't want them to be equal. Yeah, that should not be equal to 0. So these are distances of the axes. So Yeah, essentially you get a straight line, which is, it's a definitely, you would get, that would be the situation here. Your b equals 0, which is why it's called degenerate, because you kind of would divide by 0 if you wanted to put it in a different form. You get like a line. Anyway, so once you figure out who has the larger number, and it turns out that's where your circle is going to be elongated across. So your object is going to look like it's stretching to the side. It's going to look stretched out that way. How do you actually get to it though? So how you would actually sketch this is to one, plot center. Two, move A units left and right from center. Three, you would move B units up and down from center. Four, this creates a rectangle. It's not a part of your graph. The rectangle bounds the ellipse. So in other words, what I'm trying to say is, if you, here's your X and Y. So you'd have the center here, which is H comma K. What you would do is, and let's draw this in another color because I don't want you to think this is part of the graph. You move to the left and the right a distance A. And you would also move up and down a distance B. Now, what this allows you to do is this is going to create essentially a box. No, that's not what I want. Where's my blue pen? This would create essentially, I don't know if you can even see this, a box. Now that box is going to be the outline of your ellipse. Your ellipse will actually pass through this point, that point, that point, and that point. And then you kind of connect these dots. Right? So you plot the center, you move to the left and to the right by A, you move up and you move down by B. This creates a rectangle. Your entire ellipse should be bounded inside this rectangle. It'll hit these points. These guys here is called the major, this is a major vertex. And of course, this is also a major vertex. And the location of these coordinates, it's actually given in the box up here. So they actually tell you this is what the coordinates is going to look like. So it's going to be the H plus or minus this. Well, the situation I would sketch was actually this situation here. So yeah, that's how you would sketch it. You draw that box and that creates the ellipse. Now we're going to do another example of this. So let's actually just move on. The hyperbola is actually very similar, right? So the hyperbola, you notice that there's a box here. That box is actually created exactly the same way I just drew it. So for the hyperbola, create the box the same way. So that's the first step. Two, the diagonals form asymptotes. So you'll notice here in the box with hyperbola, there is asymptotes mentioned, right? So that's where those asymptotes come from. If you want to know the equation of those lines, these are always going to be straight lines. It comes from the diagonal of that box you create. And 3, the hyperbola is bounded by these asymptotes. Well, 2 points technically. So you go in and you want to sketch something like x minus h squared over a squared minus, and this is what makes it a hyperbola. Plus makes it an ellipse. So let's say you have x minus this, y minus k squared over b squared equals 1. Now, in the same way, you are going to think of this as the center. So there's a point here, which you are going to call h comma k, and you're going to move to the left and to the right by a. You will move up and down by b, which is the guy under the y. This is going to create a box. Now, in that box, you are going to have asymptotes. So if you go along the diagonal of that box, that creates a straight line, which is an asymptote. Now, if your x is the positive part goes with the a, then hyperbola touches on the side. So your hyperbola in this case, it's going to touch this point here and that point there. If the y was positive and the x was minus, you'd touch the top and the bottom. And so you'd start at this point and you'd go towards that, and then it curves and comes and goes towards that. Same thing here. This will open like that and go and open like that. So you end up with a shape that looks like either this. This is what happens when the y is the positive part. It's the first one, and then you minus the x. It opens up and down. It opens to the side if the x is the positive part, and you open the y. Well, the value of the, what if the a is positive? Well, you're squaring it here, so it's never, that's not going to be an issue. You move plus or minus a either way. You'll add a and subtract a. You'll subtract a and add a to the horizontal points, and add b and subtract b from the vertical. This creates a box. Once you create that box, you create asymptotes going through the diagonals. And if the x term is the positive term, it opens to the sides. If your y term is the positive term, it opens up and down. Right. Yeah, that's basically it. Now, in terms of being able to do some problems here, maybe I'll go through one of these with you guys, but you can try the others. But I think if we actually do just one of these, you'll get the idea. So let's look at problem 2 here. I don't know why that did it. So in Calc 2, this is the worst case scenario. And by the way, because I know I didn't want to work through all of these, I did put the answer below these. So if you actually do these, you should know what you're getting the answers here. So let's actually go through this problem. So here's what I mean. The worst case scenario, you're going to be given this in some kind of expanded form, and you're not going to actually know whether it's an ellipse or a circle. Well, you can tell it's not going to be a circle because the coefficients of the square terms are different. But you almost won't know for sure. Well, you'd also know that it's not going to be a hyperbola, but whatever. You almost don't know for sure what the curve is going to be beforehand. So if you wanted to identify this conic, state its center, and sketch it, what you would actually do is you want to write this equation in one of the forms that you would have gotten from the boxes. So here I told you the forms of all of these guys. And this is something, of course, that you should know. You should know when the equation you're looking at is a parabola versus when it's an ellipse versus when it's a hyperbola. And yeah, so you want to essentially complete the square to get it in one of the above forms. And so that's what we're going to do here. So I'm given this, I want to identify the conic. Okay, so I'm going to have 9x squared plus 16y squared minus 18x plus 64y equals 71. All right, so basically what I'd want to do is I would want to group the x's and essentially factor out the coefficient of the x squared, because otherwise I can't really do anything with that. Essentially, I want to complete the square. You need the coefficient of x squared to be 1. I would group the y's and factor out the 16. 16 goes into 64, I want to say 4 times. So that would be the first step, group the x's and y's. What you would then do is you would complete the square inside the parentheses. Move the chat window over here. So essentially you'd have x squared plus 2x. Now hopefully everyone remembers how to complete the square. You pretty much add and subtract the square of half the coefficient. So you would add -1 squared, you'd subtract -1 squared. Here you would add 2 squared, you'd subtract 2 squared. Now the guy that's in here and the x will create the first square. The guy that's inside here and the y will create the second square. Essentially, that will create a complete square. You would have x minus 1 all squared, and then this guy is just left over. That's just -1. Plus 16. Here you'd have the y plus 2 all squared, because there's a plus 2 inside the parentheses here, minus that guy. And essentially now you just want to group terms. So you'd multiply this out. And next, we would actually just move all the constants over. And so we would have, come again, 16 on the other side. What happened? Do you see what I'm doing? Did I make a mistake somewhere? Okay, so I grouped the x's, factored out the 9, grouped the y's, factored out the 16. On this side, I had a 71. Now what I have is -9 when I multiply this out. I have plus 16. So now I'm going to add everyone to that other side. So that can be 144. And then this isn't in a general form for anything. You actually had to divide. Oh, the 2x comes from this factor. If I were to expand this, I would get the 2x back. X squared minus 2x plus 1. That's what's in here. So what I would want to do now is divide both sides by 144. Now, why I would want to do that is to actually get this to look like 144 over 9 plus, where is this? Y plus 2 squared over 144 over 16 equals 1. Well, no, it won't necessarily always divide cleanly. But what we want to do is we want to be able to write this as a complete square. But no, you could get fractions in here. You could get radicals in here. So yes, the hope is that it will divide cleanly. But you want to write this as something squared. So what's that going to be squared? 12 over 3, so that's just going to be 4. So that's nice. This is going to be 12 over 4, so that's going to be 3. So in this case, they did divide nicely. So right now, how would you identify this? It's an ellipse. It fits the equation. Ellipse with the center is 1 comma minus 2. And of course, now, how would you actually sketch this ellipse? Sketch. So now you can see what I was talking about. So we're going to go down center is 1 comma minus 2. So let's say this is the x, that's the y, and we want to graph this. Okay, so first, you'd plot the center. This is 1 minus 2. That's your center point. And you're going to move 4 units in the x direction. So this means you move across 4. Was that what I was using for x last time? No, I believe I was using green. So you'd move across 4. So that would bring you to this point here, which is actually going to be 5 comma minus 2. Then you'd move 4 units that way, which this point is actually going to now be, since it's 4 units from 1 minus 3 comma minus 2. Then you're going to go in the b direction. So below the y, it's 3 units, so I would move 3 units up. This will bring me up to 1 comma 1, and then 3 units down. I don't know if that's actually drawn to scale. Well, it's not going to be drawn to scale ever because I'm doing it by hand, but I wanted to actually show how it looks elongated kind of in the right. I want you to realize that it is elongated in the x, very slightly, but nonetheless, it's elongated in the x. And then I would go down by 3 units. So this will go down till I hit the point 1 comma minus 5. And so now what this does, this creates a little box for us. And this box is going to be the thing that our ellipse is bounded inside of. And so, yeah, it'll hit these 4 points. Boom. Boom. So the drawing is much better on this thing, but it's still not perfect. Yeah, so that's going to be your ellipse. Yeah, so I would say try the other problems. If you want to actually check your graphing, tons of ways you can do it. As I mentioned, you could let's see here. Where are we? Yeah, so something like graph.tk you could use to actually check your answers. You'd probably have to write that as a function though. I don't know, would it understand an ellipse or a circle? X squared plus y squared equals 4. No, it doesn't actually have that. You'd have to actually solve for your y for that to understand. Wolfram can definitely do it though. Wolfram. So you could do something like sketch, I don't know, x squared over 4, x squared over 16 plus y squared over 9 equals 1. Now, what was it technically speaking? It was x minus 1 all squared, and then y plus 2 all squared. Yeah, so there's the sketch for you. We had something looking very similar. So it's a circle just slightly elongated in the x direction. Yeah, so a prettier picture would be this guy here. So this here is from Wolfram alpha. Right, which looks pretty similar to what we were doing here. Symbolab greater than Wolfram. It depends. There are some things I prefer Symbolab for, some things I prefer Wolfram for. I think Wolfram has more functionality than Symbolab, but there are a few things that I would prefer Symbolab for. It just actually depends. What Symbolab is good for students is that it will actually show you the steps to work out a problem for free, whereas Wolfram, you'd have to pay for a subscription. Also, and this is very weird to actually say, but whatever engine powers Symbolab, it thinks more like a human than whatever engine powers Wolfram. Like I would notice that sometimes I would type integrals into Wolfram and it will give me this really complicated answer. And I'm like, it's just a substitution problem. What the heck did this computer do? And the computer probably used some kind of series approximation or it uses something where a computer would really be good at doing it. But if you go to Symbolab, it will literally tell you, oh, we did a substitution, u equals this, and then blah, blah, blah. And so sometimes I find that Wolfram just goes a way that's too complicated for a human being to actually do. And so the answer comes into a more complicated form. So there are times when if I type an integral and I realize in Wolfram alpha, the answer just seems way too complicated. Like there's no way that that's what was meant. Sometimes what I do is I would just actually check Symbolab, and a lot of times the answer actually looks simpler and it actually looks closer. So sometimes if I'm writing a test and I'm testing I'm writing out the solutions and I check it on Wolfram just to make sure I didn't do a typo, and it's like, what? My answer doesn't look anything like that, but then Symbolab would look exactly like my answer. So yeah, Symbolab follows Jhevon's strategies for doing integrals, it seems. Yeah. Anyway, that being said, there are some times where the engine in Wolfram is more powerful. I've seen Symbolab run out of computation time on things that Wolfram can actually compute. And I think that's because Symbolab is working like a human and as opposed to a computer. Yeah, in terms of notes, I always post the notes. When I do lectures like this, I post the notes in the description box. So if you look at the last video, the notes are in the description box. Yeah, so sometimes I go back and forth between Wolfram and Symbolab. Anyway. Yes, in YouTube. So when I post this video and all the videos that I've done on the OneNote, I do post a PDF of the notes in the description box to the same video. So yes. So yeah, that being said, so major announcements. I will not see you guys until the 15th. So you guys have a week to relax. I'll see you here again on the 15th. And tests, I still don't know what we're doing for tests. I am going to go bother people in the math department again. But yeah, so for now, practice this, get the notes from the description box and read over your things slowly. And yeah, stay safe, everyone. And I suppose nothing else to say, but a nice lecture number to end at. Yeah. Yeah, I did ask about teaching Calc 3, by the way, which it doesn't seem very likely, I'll just say, because of how things are. I think they want the people who taught in the spring to teach the same classes in the summer, because they would have already created online notes and stuff. But we'll see. I asked for Calc 3. We'll see where it says. Anyway, goodbye, everyone. I will see you guys. Stay safe. I teach linear algebra sometimes. I haven't taught it recently. That's another class that actually changed the syllabus recently. So linear algebra right now is a lot more computational than it used to be. Last time I taught it was very proof-based. I do teach 391. That syllabus is pretty much the same. So my YouTube videos that I did for 391 last semester should be pretty useful to you. Pretty much everyone who teaches that class would teach what I taught in those lectures. All right, yeah, you guys have a lot of work to do. I guess you can take a little break, all right. But good night. I will see you guys. Take care. And let's stop this thing. All right.